So welcome back to our class. We just continue what we were doing last time. We were looking at how knowledge proofs in Noir. And of course, I've been doing all this time. So trying to just to ensure that our skills in how to do these zero knowledge proofs. Just improving on our skills. So last time we looked at how to prove that how to prove given two numbers. No, not how to prove that we can get factorization of a number. Given a number, let me say, for instance, two numbers that give us 49. So the prover, you as a prover, you know the two numbers, you also know the product, but the verifier only gets to know what the product is. So we did generate a zero knowledge proof just to do that. In this case, our two numbers A, B remain the secret, and we only reveal the product. So that's what we did last time. So today again, we want to look at different, but just the same thing. So because no, what that means. The same thing is we want to show some statements to bring to light some other stuff which maybe the program has to get to know. What I was doing, I was just explaining what our topic is. We'll be bringing some information to light, and the other information remains our secret in our zero knowledge proof. So we all know what Noah is and how, of course, he's very good at writing zero knowledge proofs. The fire has to be told what the public is and is denied information, and information is our secret. So today we're just moving into selective disclosure, just as the same thing. How can you prove secret numbers without revealing them, but share only certain public facts? That's what it means by Noah in the shadow. So we just want to reveal some facts, expose some facts to light, and the others just remain our secret. So I had already done this recap of what we did last time. We did the compositeness, whether we were revealing, we are proving, we know two numbers whose product will give us another number. So this other number, the opposite, we were revealing to our public input. So we are revealing this to the verifier. So what we did last time, that's a recap of that. Still the same thing. So today we want to go slightly deeper, just a bit. Of course, still related. My internet is poor today.
Oh, okay.
Yes. Now, today, we want to want to show that we know two numbers, X and Y, whose product is 42. But now the only thing we reveal to the verifier is the product of, no, the sum of Y. The sum of X is what we will reveal. We're not revealing 42. We're not revealing X and Y, but we're giving him the sum of X and Y. So as I was saying, numbers 7. So let's say we know numbers whose product is 2, and give you the sum of those two numbers. We say we give the sum 13. So supposing our number 6 and 7, we are giving you 13. So that is our public value that is what we make public, 13. So we are not making 42 for not public this time. X and Y are not public, but their sum is public. Our goal today, we just we have to tell you, we tell the prover, not the verifier, we know two numbers whose product is 42. But then we just expose the sum of the two numbers. So that if the two numbers are 22, 21, and 2, we are telling you, you know, these two numbers, and their sum is 3. So that is what we'll be doing today. So that is just a slight addition to what we did. So this time, our private, as I've said, our private inputs will be X and Y. And then we have the public, which will be their sum. And then our constraint is X times Y is 42. But this 42, we are not revealing it. We are not saying that this 42 is a private, or it's not public. That is what we are doing. Our only public thing is X and Y. So this will be our circuit, therefore.
I am not seeing a screen.
Yes.
Are you sharing the screen?
Yes, I'm sharing. Maybe it's because of the network. Let me again unshare and then share.
Okay.
Just today I have a problem with the internet. Can you see?
Yes, now I can see it.
Okay. I just shared, I had already talked about this. Generally, we're going to do a proving that we know two numbers whose product is 42. So you can always change this 42 to another number, because once we write a circuit, we can always change this circuit depending on the functions. So you can always change 42 to another number, but then the way you write proof and the same thing. So our private inputs will be X and Y. Our public input will be X plus Y. So that is what we'll be exposing to the prover. So this is how you can do. The main X is private, Y is private, and then our public value is what we're getting out. And see pub field. Pub field, it means the field coming out of X and Y, that product. It's written as sum. So let the sum of X and Y. This is our public. This is what is coming out. This is what the result is. The result is this. That is our result. So this is therefore what is public sum. What we mean therefore is that we have 42. So there are several numbers that give us this product 42. So the very there. And of course, if you're doing zero knowledge proof, or two here, this value will be picking a bigger value, not as small as this is for our practice. Now it might be larger value. So now this I will not get to know whether our values are this, whether we use that, whether we used this, whether we used that, and so now these are just few options. The verifier may want to just check any of the options and see which one works. And so he will get to know what X and Y is. So, but we are saying we then use for bigger value here that we have several options so that verifier is able to check each and every option. But if you're using smaller numbers like this, it's very easy for the verifier to do this. So supposing our two values X and Y are 6 and 7, what is public is their sum. Just saying that we know two numbers whose products for 2, but then we give you the sum of two numbers, just like that. So if these were a bigger value, then it becomes very difficult to use brute force. Check all the possible values, get what X and of course, again, if you supposing you discover, you say that you suppose you use brute force and get that the two numbers are 7 and X and 6, you may not even get to know which one is X and which one is Y, because again, that is our point. We are making them secrets. You don't need to know what X is. You don't need what Y is. So even if you may get using brute force, you may not exactly know what our X is, what our Y is. So this is how our circuit looks like. The only thing we add now will be the test, just to confirm that our main function is working properly as designed. And then maybe, yes, just that, just adding tests as what remains. So the verifier and it will be able to see the proof. The proof the verifier will be saying will be that X times Y is 42. That's a proof that the verifier will be seeing. And then gets to see what the sum of the two values are. But the two values remain private. So to test, you just want to assert that the sum is correct, the product is correct. So for instance, if you have 6 and 7, it's true that their product will be 42 and the sum will be 13. So this test is supposed to pass. If you have 21 and 2, their product will be 42 and their sum will be 23. And again, this is supposed to pass. But if you have these two, of course, the product is supposed to be 40. So this one is not supposed to pass. This will fail. This is an invalid, the product is invalid and therefore is supposed to fail. So if you want it to pass, of course, we know how we normally write it, should fail. So when you put like that, should fail, then we expect it to pass. Expect it is to pass. Now, so you can change also have these two values correctly, like 6 and 7 correctly, and then try to give it a wrong product and see whether it passes. Of course, that is supposed to to fail. The two numbers are correct, but now the product is wrong. And the other way you can also change, you want to see whether it, you see when you're writing this test, you want to see whether your circuit would, the main function is properly functioning. So you may want to give it also the right product and give it a wrong sum and see whether that test passes. So it's supposed to fail if the sum is wrong. So that if your tests pass, the ones will be designed, if they pass correctly, then it means the proof you generate will be correct. So that proof can never be wrong. So I don't know whether you had cloned it.
No, not yet. Let me go to the GitHub and maybe try to find.
Yes, it's just called it's called a product and sum circuit, I think. So just confirm. Are you able to do it?
Just a moment. I'm almost done cloning.
You have seen the ZK proof?
Yes, I've seen it.
Multiplication and okay. Yeah, you can clone that and also clone the next one, which is Noah's ZK affine relation.
Okay.
Because that will be the next one. Yes. We are doing those two.
Okay. You've said the other one is
the Noah ZK affine relation.
Okay. Yeah, I've cloned the first one. The second one is still cloning.
Okay.
The second one is still cloning, but the first one is done. So maybe we can start
Okay.
with the first.
We can begin. Okay, you can share.
Yes, I can share. Yeah, can you see my screen?
Yes, yes.
Okay, yeah.
Okay, this one is yes, it's the same one.
Yeah.
Yeah, so you can see our main function. We have X and Y, which are private, and then the public value is what comes out of that is our result. Our result is and it's our sum. Okay,
Yeah.
so our tests, you can see our tests there. The first test is true that 6 times 7 will give us okay, I was not giving, but if you change any of those values, it will not accept because we've already done in our main function, we've already said the assertion that the product of the two numbers is supposed to be 42. So the two numbers, X and Y, they must give us 42. That is the assertion. So let the sum be the sum of X and Y, and then assert that it must be 13. So that is, if you change that sum again, it will not run. So you can see even there's a test for the negative values. And again, the sum should be correctly captured. For instance, that -6 and -7, the sum should be -13 and is well captured. Okay, so let's just try to run those. Let's try by Nago compile. I'm sure this time you very much good at these things. Or you get
I
into
need
circuit.
to, yeah.
Yes, yes.
Yes, now we have our target.
Yes, and we have that, our ZK proof dot Justin. Okay. So you can also now see what is in the build.sh.
Okay.
What it will be doing for us. Compiling. Then it will be giving us the verification key using the command bb-write verification key. And that verification key, it's supposed to use the .json that we just created. And so why we put the first bit of compiling is that if we had forgotten to compile, it's supposed to do the compilation itself because it requires the .json to be able to come up with the verification key. So that part, the first part, compiling circuits, is just meant to ensure that that .json is already in the target because it has to be used. But if you remove that, it will still compile, but that one means you have to do Nago compile first. But as it's designed now, if you forgot to do Nago compile, it will do it itself and then use the .json to create verification key and then store it again inside the target. That is the first function it's doing. Then the second one is using our command in line 17 to create a verify.sol. Okay. So to get the verify.sol again, it uses the verification key. That's why you can see we've written there target verification key. So it requires that verification key first of all. So that is why the first part we did compile. The second part we did verification key. Then the third bit is verifier.sol. So in that order. Yes. So let's run it.
We run the build.sh.
Yes.
Okay. Oh yeah, yeah. So certificates. Yeah, so it has worked, and now we have our verification key. Here it is. It has been saved here, and then we have the Solidity verifier contract. I think it should be here.
Yes. 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 It's there.
Yeah.
Good. Now, you've seen that how we write this build.sh is just the same. We are only changing the name of our project. For instance, yes, you can see that we've just written ZK proof multiply. That is the only thing we are changing. The rest just remain the same thing.
Okay.
Yes, even this part for generating the solidity verifier, this one is just the same for all that we've done. Yes, just the same. Now, the other thing that is just the same again, if you go to JS, you will see that, yes, generate proof .ts has been the same. We're only changing the name, line 3. Line 3, we are changing the name of our project, and you can see the name there is ZK proof mult and sum. So that is the only place we are changing. Then we come to down there. No, not there. Line 13. Line 13 and line 14. We're just inserting what is in our prover.toml. What is in our prover.toml? Yes. That is what we are putting there. So there's nothing we are changing. It's just that. The rest just remains the same thing. And we've been using the rest just as it is. Just been changing that bit only. The other bits have just been the same. So the other thing that maybe we may again want to change a bit is that Cyprian verifier app in the test. Is that one. And that one, what we are changing is maybe from, yes, at that point. So giving us, that one we're just putting, how many public inputs do we have? So in our case here, our public input is just one, because we are only outputting, the public output is just the sum.
Yeah.
So if there were to be two public inputs, that is the point we would have changed. If there would be 3, again, would have changed that point to 3. So we're only changing, and again, if you want to rewrite this thing, maybe you can only rewrite from line 25 to line 33. You may want to rewrite it in another form, but to do the same thing. Yes, but the rest just remain the same. The other point, maybe if you want to rewrite again, you can want to change that line 18. Like in our circuit, this time we are just proving the equality. We are proving the equality, but at some point you may not be proving equality. So when you are not proving the equality, then you may want to change that point. When you're not proving equality. In our case, we are proving equality that this product is equal to this, or these two numbers, they sum up to this. So that is why we have equality there. But in some of our circuits where we've not had equality, we've always changed that bit. So the other bit that we may want to change will just be in the test. When you click on that test, yes, the starter.t.sol, and you're only changing line 12. In our case, we only have one public output, so that is 1 there. If there were 2, we would write 2. If there were 3, we would write 3. And then if there are 2, we come to line 17. Line 17, you can see we have public input 0, and then our public input is 13. So supposing we had another public input, let's call it 17, we'd create another line 18, create another line just below that, we press enter, and copy the whole of this, and change 0 to 1, and change this public input to the one that we want.
Okay.
Yeah, so those are the only things we may want to change in the whole of this thing. The rest remain the same thing. Okay, so let's go to our JS and then generate the proof. Yarn generate. So we get out of circuits.
Should I do yarn install first?
Try to see if it asks for that, and then we will. If it asks for that, and then we will just install. Just try, but get into JS first of all.
Oh yes. Yarn generate. Generate. Oof.
Yes, there's a hyphen. Yes. Oof. Okay, so okay, then it means install.
Yeah, so it says the proof has been generated successfully.
Yes. And where is it? You can see it inside the target.
Yeah, it's here. It's here inside
you can see
target.
It there, and then the public input. Click on the public input. You can see our public input is D.
Yeah.
Is one public input and it's D. D is 13. Because as I said earlier, normally this one does numbering in hexadecimal. Hexadecimal, we have 1 up to 9. Then A, B, C, D. So 1 up to 9, 10 is A. Then 11 is B. And then C.
And then D.
Then D, 13. So that is our
okay.
Yes,
I never knew that. I just thought it was just
Yeah,
a representation of it, but now I get that, it's actually
yes,
13 because it's D.
yes, it's hexadecimal.
Okay.
Okay, so after generation of the proof, the next thing is to verify the proof, and we are doing that in our contract.
Yeah. Hmm. Mhm. Yeah. So we do this, we use this command over here. Command copy. Yes, it has verified. Hello.
Yes, I can see.
Yeah.
Can you hear me?
Yes, I can hear you.
Yes, it has verified proof. Read the way using the style. Of course, so we begin.
Your voice is breaking. I don't think I can hear you. Can you hear me?
Okay.
We were here.
Yes. So we had just generated, verified the proof. So let's generate this proof in another way. This time,
Can't hear you.
can you hear me?
Yes, now I can. I was not hearing you.
Okay. We'll go to our circuits and do Nago compile and execute, because we want to generate the
Okay.
proof in another way.
Okay. Now go execute.
Execute.
Hmm?
So we have a witness.
Yeah.
Okay, so the next thing we can do now is to generate the proof. So the command is in our README for generation of the proof. It's there.
This one. Okay.
Yes, because want to generate the proof in CLI. That is
Right.
another way of generating it. So you can always use one of these ways to generate the proof, but as we are doing the two, just to confirm that we have the same proof. And you can see we have a proof. The same proof, but now the public inputs. The first one, okay, click on the public inputs. That
we
is
have this
when
one.
Yes, click on that.
We have this one.
Yes, that one will not be visible.
Yeah, it will not open.
One, yes, if you want, you can do cut something, cut, and then you get it. And it will be the same. It will be the same. Okay, so these public inputs have been generated by that command. That is the command that has given us a public input. But the proof will be the same. That is why we don't have, it's just at the same point, we just the same proof. Again, we can verify it in the same way we did the earlier one.
Yeah.
Let us verify.
We will use JS to verify or?
No, just the same way we did for JS, we go to the contract and verify using Forge.
All right, so. The command was here. This one?
No, it's 52. That is the same command we use for verifying.
Okay.
Yes. So just now verifying this second. So it will be, you see, our proof has the new proof we generated. So if it were wrong, this verification will not work.
Okay.
If it were wrong, the verification will reject. It will reject. For instance, if you want it to be wrong, we can go to, if you want it to be wrong, let's try go to test starter.t, starter.t.sol. Okay. And then change even line 12, where there is 1, write 2.
Okay.
And then let's now generate the proof. Let's go back to circuits. Execute. Generate the proof. Yes. The proof has been generated, huh?
Yeah.
Okay, let's verify it.
Yeah, it says that there's a failing test.
Yes. So you can see the proof was generated correctly. But now when we try to verify it, it does not.
Yeah.
So there are things that are not matching.
Yes.
There are things that are not matching, so it will not. So let's just return that to 1, back to 1. So that's why I was saying the fact that the proof that we generated second, it was able to generate and was verified. It means it was the same as the earlier one.
Yes.
It was the same as the earlier one because our proof is already inside the verified.sol. So the verified.sol, when we run the verified.sol, it already has all these details. Now, when you try to run a proof and you get a different proof and verify, it's verifying against the verified.sol. When it finds that they're different, it then fails. It then fails because the proof generated must agree with what is already in the verified.sol.
Yeah.
So let's again do it now so that we have our test passing.
Yeah, test pass.
Okay, so let's proceed to the second example.
All right, let me see if it finished. Yeah, it's actually finished. So let me open.
It finished, huh?
Yeah, yeah.
Okay, so you can again just share.
Okay, just a moment. Yeah, there I have shared.
Now, this is a very good circuit also. We have three constants which the prover exposes. So the verifier gets to know what A, B, and C are, but X is kept secret. So you can see X is private, A is public, B is public, and C is public. So we just want to show that A times X plus B would give us a C, but X is not revealed. So you only give the verifier ABC. So we assert that the product of A times B, not A times X added to B will give us C. So again, this can be customized and applied in several areas in privacy proving. You can customize and apply it. So let's at our tests. The first test, we have X as 5. You see, we're just telling the person that A is 3, B is 4, C is 19, and we keep X our secret. But now, when we do our assertion here, it should be seen that 5 times 3, which is 15, when you add 4, you get 19. It must satisfy that condition. Then the second one again, this one is supposed to fail. You can see 4 times 3 will be 12. Then plus 4 is supposed to give us 16. But as we've said, C is 19. So that means this must fail. And even the other one is supposed to fail. No, this one is supposed to pass. Supposed to pass because that would be -4. -4 plus 6 will give us 2. And so it's supposed to pass. So I was just seeing whether our main circuit can also function when you use negative values. And that is how you do when you're writing, you try all possible tests and see whether your circuit is responding to all of them correctly.
Yeah.
If it doesn't respond to any of them correctly, then you have to rewrite either the tests or the circuits correctly. Okay, so let's look at our prover.toml. Okay, and so again, I just want to take you to JS, and you see that what is in our prover.toml, what is in our generate proof.ts. You can see it's the same. We've only changed the name on line 3. The rest are the same. Okay. Now, our public inputs here are 3. Let us go to our tests and confirm that we have those 3, our tests in a contract. Okay, tests. Yes. And you can see there are 3 there, line 16 to line 19. That is the only place I changed, and then I changed line 12. line 12, you can see I've changed and said our public inputs are 3. So the other place we did change, as we said from the beginning, is on Cyprian verifier.app, verifier app, and it's just at line 27. That's why I changed, and I said the length would have 3 public inputs. The rest is just the same things. The rest will just be the same. And so we can now do our build.sh, because we know it will do Nago compile. So you go into circuits and do it. Okay. So your verification key there, and the .json is also there because it required it. So it had to generate it first of all. So again, after that VK, we have also verifier.sol generated inside our contract. You can see it, huh? Yes, they're verifier.sol. The 7th line of the verifier.sol, the 7th line has captured our public inputs correctly as 3. So that is why I was saying, and again, you can see from line 11 to line 13, our public inputs have been captured there at 2, 5, and 3. No, 5 and 3, is it? What is that? Oh, one is the circuit size. Circuit size, and this is log size. And this other one is public input. Our line 13 is the same as line 7. Just respond it line 7. Okay. You can go down. Just, okay, that's the same verified sol. Just want to see our contract at the bottom. Okay, it's there. Number of public inputs, part of that. You can see n log n, number of public inputs. So these ones are just coming from the top. We had such things from the top, and now are in our contract, the summary of our contract. Okay, so let's generate the proof. Okay. Okay, and again, that has been verified. So our proof is correct. It has been verified. Let's go to the Cyprian verifier.app, the app, and change that 3 to 2 and see whether it will work. Okay, try to verify again. Okay, it says expected 3 public inputs. Expected 3 public inputs, but it's seeing something different, seeing 2. So return to 2. So that is what was it. Return to 3. That was what was expected. Anywhere else we can change. Go to the starter.sol. Now change line 17. Line 17. Just even where that 0, make it 1. That 0, make it 1. And try to verify again. Just try to verify. Let's see. It says failed. Some check tests verify proof. So that is okay. So make it 0 back to 0. So you can see anytime you make a mistake, it will detect. 19, make it 18. Let's see. 19, make it 18. That is on line 19. On line 19, change that to 18. And try to verify. Again, it fails. So return it to 19. So it means you can never lie. You can never lie in your proof. I saw a post where somebody was asking, I don't know whether it was you posted, somebody was wondering whether the proof that is given by the prover, whether it should be, somebody should trust it. I don't know whether it was posted in our wall or somewhere else I was reading. That how can the proof which is generated by the prover, why should it be trusted by the verifier? So maybe the person was thinking that again, okay, the prover can lie. You cannot lie.
Yeah, you can't.
That proof, although it's, oh yes, although it's the prover generating it, the verifier is supposed to accept, because if it's correct, the prover can never try to lie. You try to lie, it will not be generated.
Yeah, and also one was asking also who verifies the verifier. Now that the verifier is verifying the prover, now who makes sure that the verifier maybe may not cheat, but you know, the aspect of completeness where if a prover is very honest, then the verifier should also be convinced. And if they are trying to cheat, they can never convince the verifier.
Yes. Yeah, the verifier is just is not being verified. Nobody's verifying the verifier.
Yeah.
You see, the verifier has a problem because it's him that wants to know whether you really know what you are saying.
Yeah.
Yeah, it's the verifier that is very much wants to actually prove that you know what you are saying, what you are saying you have. So for him, he has no room to lie. What he just wants is to get, he just wants to get information from the prover. Wants to get the information, and he wants to be convinced that the information the prover is giving is correct.
Yes.
So that's what he wants. So if it's like an ATM machine and it wants to give you some money, it just wants to be assured that the password is indeed yours. That the password you're giving is yours. And once you give the correct password, and then the machine is supposed to give you the money.
Yeah.
Yes, supposed to. So the machine has no room to lie. It's not lying about anything. It's just supposed to consume the information you're giving, see that the information you're given is correct. And if you're trying to lie, the information will not, the proof will not satisfy. The verifier will not be satisfied by your proof. It will be a wrong proof. And so the verifier from his end can see that you are trying to lie.
Yeah.
Yes. So that is what happens. You can never try to lie. If you try to lie, we already generated the proof. But now we want to verify the proof. We are now the verifier. We are now the verifier. We wanted to verify that proof. The proof has been generated. We try to verify, it refuses. Because some of the values are not correct there. So they have to be correct. Once they are correct, the verifier will just be convinced. Once he proves, he runs the proof, the verification, be convinced that that proof is correct.
Yeah.
Yes. I think we can stop at that unless there's a question or unless there's another contribution you want to make.
No. Actually, so you remember the one you were working on, Noir modular exponential?
Yes.
I sent a PR there for just adding some more test cases. Yeah. Maybe if you could check it out. It's just a simple one. I just added maybe 2 or 3 more test cases to that circuit that you were writing that day.
Okay. Or you have it on your machine, huh?
Yes. Let me try and see if I can open it. Just a moment. Let me share that window. Yeah, I think it's this one. I think I added test with exponent of 1. I think I think I added, I don't know if I added this text with exponent 0.
0, so that gives you a result of 1.
Yeah, and then I think I did I think I did also modulus 1. I don't know if this was here.
Where the mode is 1, eh?
Yeah, I
5
think
raised to 3 mode 1. Okay, when you run it, what does it give? When you say Nago test?
Okay. Yeah, it was working. Oh, let me read into circuit. Yeah, so all of them are passing.
Okay, 10 of them are passing.
Yeah.
Yeah, that's correct. So when you're writing this circuit, the only thing you want to verify, sometimes you want to eliminate some weird values. For instance, mode 0. So you want just to ensure that if somebody does mode 0, it rejects.
Yeah.
Mode 0, because mode 0 will mean division by 0. So you just want to ensure that if you write mode 0, it rejects. But if you try and find that you are writing mode 0 and then you run and then it passes, it means you have to some constraints.
Yes.
You have to rewrite the circuit such that it can reject division by 0. Yes, so that is the only thing you may want to try. later on, try to write a test where mode is 0 and see whether that succeeds.
Yeah.
If it succeeds, it means you go back and try change a few things.
Yes, so you can look at the PR. I think I already submitted it into this repository.
Okay.
Yeah.
You submitted it to?
This repository, I did a PR on this repository because it's your page.
Oh, okay. I don't know why I have not seen it. When was that?
Let me see into my GitHub. Let me see when I submitted it.
I have not received an email because when you do a PR, you're supposed to get an email directly.
Let me show you. Let me share this one.
Okay.
Yeah, this one I did here. I did exponent of 0, exponent of 1, base of 0, and base of 1, and modulus of 1.
Okay. What is the top? Let's look at the top.
This
okay. Yeah, I can see the modular exponentiation. Okay, just at the bottom, after you've done that, just scroll at the bottom. In the comment section, you can just write something there so that you see you do at yes at Cyprian Sakwa. Review this.
Okay.
Yeah, so that one now gives me an email directly. I can easily go there and check.
Okay. All right.
Let me just check the email if it has come. If it has not, then it means again my GitHub may have been compromised. Somewhere they have compromised it.
You should add 2FA if you haven't.
Yeah, I can see now it has come. Let me just show you. You can just unshare. I show you now how it comes after you've done that. I'm able to see it, but otherwise I had not seen it.
I also think that's the reason I also submit PRs to most people and maybe they don't see them.
Yes, it's just good that you try to inform them. And so now I can see this. Yeah. I can see this. So when I come here, I just click. I click on that. Then when I click on that, I can see I left a comment on model exponentiation. I take a look at this, apply this on GitHub. So I may even want just now to come directly here and go to where it is. And now I see.
Okay.
You can see what I'm seeing.
Yeah.
Yes. I can see you've 2 checks. You've changed one file. And this will be the test file.
Yeah, I just added a more descriptive. I added this one here. Then I'll just add in more comments.
Yes.
Yeah,
So I
now
can
I
see
added
that.
the test.
Yeah, so when you do that, it becomes easy.
Yeah.
It becomes easy for somebody to follow.
Oh, I think now I will go to all those repositories that have submitted a PR and just do art because I was always wondering.
If you can know who the maintainer is, you just go through and see who the maintainer is. If you can know who the maintainer is, you can always try to write to them. But some of these other GitHubs, the maintainers are always checking. The maintainers are always checking, and therefore they can always see and make those. And so sometimes they just take time, especially we have some GitHubs where you find that we have so many issues unresolved. So they have so many of them. They are taking a lot of time to resolve. So they'll just reach on and resolve. But it's always good again if they take some time to remind them.
Yeah.
You see, like without that message you wrote, let me show you how my GitHub is, and you can see that there was no way I was going to know that you had done anything. Look what this is how it is. So when it's like this, there's no way I can get to know that you have done anything.
Yeah.
Now, if I was to come, this is where you did.
Yes.
Yeah, so look at how it looks. I cannot tell that there is any request here. But let me just check on the overview. Maybe I need to see some pull requests. You can see again at the top side, I only have overview, repositories, projects, packages. You can see what I'm sharing, yeah?
Yeah.
So there's no hint that some pull request has been done.
Yeah.
There's no hint. But now if you were to write to me a comment as you did, I can now follow and go straight to where the comment is directing me to. From there, I can be able to, but without that, I cannot actually tell. You have to open every and all these to be checking all of them inside. But now that is why I'm saying, like these other repositories, you see when I open this, I can now see there's a pull request.
Yeah.
Now, why these other repositories they're able to see is that they maintain their repos every day. They come, look at their repos, do a few things here and there, trying to maintain them. So in the process, they're able to see there's a pull request.
Yeah.
So if you never left a comment, they're able to see there's a pull request. But for us who don't maintain our repos on daily basis, it's not busy. Yes.
Yeah.
Yeah, without a comment, it's not busy. Okay. That's okay.
Okay.
So this is the pull requests. I can see it's yeah. So if to come out there, ask look at this, and then you choose what you want to do. Or if you just want to merge, you just say merge. And confirm the merge. Just confirm the merge. And once you do that, it's supposed to change and say merged. So this thing is supposed to change to, you can see it has now changed to, is it purple?
Yes. Yeah.
Yes. So it's good always you leave a comment. You leave a comment. So just go through all your
pull
PR
request
and write some comments just to so that they are able to see.
Okay.
And always be trying to find out who the maintainer is. So so that the comment goes to the email of the maintainer.
Okay.
Yes. It's okay. So I think we can end at that.
Yeah.